Now that we understand vectors, let's try and understand what linear transformation of these vectors mean. We all know functions. So y is equal to x square is a function. What this means is that for every value of x, there is a corresponding value of y such that y is equal to square of x. Similarly, if x belongs to a set of real numbers, then this means that there is also a corresponding set of real numbers called y, which is a square of x. In other words, this function is transforming certain scalar values, which are in one dimension, to another set of scalar values in the same dimension. So this transformation need not always be from one dimension to one dimension. You must have seen such certain functions like, say, for example, if you want to calculate the price of the house, the price of the house is dependent, say, on the size of the house and the age of the house. Say 6,000 into size of the house minus 1,000 into age of the house. Now this specific function, what this is doing is, if I give you a housing data set which is in two dimension, which contains the size of the house, a two-dimensional vector which contains the size of the house and then the age of the house, and pass it to this function. This function outputs me a scalar quantity called price, or I can call it as a one-dimensional vector, such that this price is derived using this specific equation. So in this case, this function is transforming a two-dimensional vector into a one-dimensional vector. Basically, these functions are simply transforming elements from an n-dimensional coordinate space to a m-dimensional coordinate space. Therefore, this association or mapping is also called as a transformation. So going forward, these functions, instead of representing them as f of x, will represent them as t of x. Now, what is linear transformation? The definition says that for a particular transformation to be linear, it has to satisfy two conditions. This t of a plus b, that is transformation of two vectors a and b, should be equal to t of a plus t of b, and then transformation of a scalar c multiplied by a vector a, let's call these vectors, should be equal to c into transformation of vector a. Let's take an example of function f of x is equal to x square, which we talked about earlier, or rather let's call it a transformation. Now does this transformation satisfy each of these conditions? Let's put this in the first condition. So what this says is a plus b whole square should be equal to a square plus b square, which is not the case. Therefore, the transformation t of x is equal to x square is not a linear transformation. Similarly, if we take another transformation, a t of x is equal to 2x plus 3, and if I put this in this condition, what this says is 2 into ca plus 3 should be equal to c into 2a plus 3, which is again not the case. Therefore, this transformation fails the second condition. So neither of these are linear transformations. Now we looked at two transformations, t of x is equal to x square and t of x is equal to 2x plus 3, and called both of them as not linear transformations. Let's take another transformation, t of x is equal to 2x. Now applying the first condition, 2 of a plus b should be equal to 2 of a plus 2 of b, and which satisfies this condition. Similarly, 2 of ca should be equal to c into 2 of a, which again satisfies this condition. Basically, what these trans so now we understand that based on these conditions, we can identify which transformations are linear and which transformations are not linear. But what do these conditions intuitively mean? What this basically means is that the first condition means that once after the transformation, if there is a vectors representing straight lines, these should remain straight lines which are This is the reason why the transformation x square is not a linear transformation. Similarly, the second condition says that the origin should not shift. That's why the transformation 2x plus 3 is not a linear transformation, because after the transformation, the origin shifts by 3 units. So just to summarize, a transformation is a linear transformation if lines remain lines, and 2, origin doesn't shift after transformation. Okay, so all this math is good, but where do we use linear transformations? You actually see linear transformations in your everyday life. You see them in computer graphics while playing games. You must have seen objects rotating, zooming in, zooming out, stretching. All that is linear transformation. You see shadows of objects or object being viewed from different angles. All that is also linear transformation. A shadow of a 3D object is nothing but transformation of the object from a three-dimensional space to a two-dimensional space. Now let's understand the linear transformation using a simple example of rotation transformation. You have a two-dimensional coordinate space here, and there is a square within this coordinate space. And you also see two unit vectors. One is in x direction and other is in y direction. The x direction in green and y direction is in orange. These are unit vectors. This is 1, 0 and this is 0, 1. Now see what happens if I apply rotation transformation on this. What you see here is as soon as I applied rotation transformation, the unit vector which was in the x direction, the 1, 0 vector, has now rotated from 1, 0 to 0, 1. And the unit vector in the y direction earlier, which was at 0, 1, has now moved to minus 1, 0. If you go through this slowly, you will see that all the lines have been rotated, but all the lines still remain the lines, and the origin did not shift. It's at the exact same place. So this is an example of linear transformation. Basically, we are rotating not just the shape, but the entire space in which the shape lies, so that the shape moves along with the space. Simpler analogy would be, assume that this entire coordinate space is a piece of stretchable cloth, and then this square is a pattern which is stitched on that specific cloth. Now, if you rotate the entire cloth, the pattern also moves along with the cloth. If you stretch the cloth by holding on the four sides, then the pattern also stretches along with the cloth. So that is what happens in linear transformation. We manipulate the entire space so that whatever objects which lie within that space also get manipulated along with that space. These transformations need not always be in the same dimension. For example, if you see cube here, we have unit vectors representing x, y, and z axis. But once the transformation has been applied, the cube converted it to a plane. And now the z vector has been squashed into the xy plane. So this is how you see shadows of 3D objects in games that you play, etc., by applying the linear transformations. Also, as you can see here, a particular object can be viewed from different angles by applying a linear transformation. Now these transformations, when you visualize them, we know where the points prior to the transformations were and where they have landed after the transformation. When I have multidimensional objects which have many vectors representing the edges of the objects, if I can understand where these edges fall after the transformation, then I can easily understand what the shape of that object would be after the transformation. How do we easily do that? How do I figure out where a particular vector lands after the transformation is applied? Now think about this. If you have a vector in a two-dimensional coordinate space 1, 2, what this actually means is that in a xy plane, this vector is 1 unit magnitude in the x direction and 2 units of magnitude in the y direction. So if you have two-dimensional space, has unit vectors 0, 1 and 1, 0 as your basis vectors, any other vector 1, 2 can be represented in terms of these unit vectors as 1 into the unit vector, that is this 1 unit in the x dimension plus 2 units in the y direction. So when a transformation is applied on this vector 1, 2, transformation applied on vector 1, 2 can be written as transformation applied on 1 into the x basis vector plus 2 into the y basis vector. Now based on the linear transformation condition, we can write this as 1 into transformation of 1, 0 plus 2 into transformation of 0, 1. Now this is very important. Think about this. What this is saying is that you can find the transformation of any vector, that is you can figure out where the vector lands after transformation by simply figuring out where the basis vectors or the unit vectors in each direction land after transformation. So if we look at this transformation, we know where the basis vectors landed after the transformation. The vector 1, 0 landed at 0, 1, and then the vector 0, 1 landed at minus 1, 0. Based on this, we can figure out where any other vector lands. Say vector 2, 2, it should land at 2 into 0, 1 plus 2 into minus 1, 0, which is equal to minus 2 and 2. So as you go along with the transformation, the point 2, 2 which lies here initially, you can track and see where it lands finally. So the point 2, 2 which was here initially, in the transformed coordinate system, it lies here at minus 2, comma 2. So if a unit vector 1 in a two-dimensional space, a unit vector 1, 0 transforms to a, b after the transformation, and unit vector 0, 1 transforms to c, d after the transformation, then any other vector x, y transforms to x into ab plus y into cd. That is equal to ax plus cy and bx plus dy. This is the vector at which x and y lands after the transformation. This can also be written as ACBD, matrix multiplication of ACBD with a vector xy. AB represents the new vector at which the x unit vector lands, where CD represents the new y unit vector. So basically what this tells me is that I can simply figure out where any vector xy lands by performing a matrix multiplication of xy with another matrix ABCD, and the resultant gives me where the unit vector xy lands. So whenever you see a vector or a matrix of vectors being multiplied by another matrix, all that we are trying to do is a linear transformation, or we are trying to manipulate the coordinate space in which vectors are present in order to transform those vectors into a different form. Think of the rotation that we have seen, or maybe stretching, zooming, zooming in, zooming out, etc. Hope with this you are clear about what linear transformations mean and how linear transformations can be performed and what the uses of linear transformations are.